Have you ever looked up at the night sky? Have you wondered where it all came from? Imagine a time before stars, before planets, before anything we know. What did the very beginning of everything look like? It is a question that has puzzled humanity for centuries. We try to picture a moment of creation, a point where our entire universe sprang into existence. This is the ultimate origin story, the birth of space and time itself. It's a concept so vast it almost defies our imagination. We are trying to peer back to the dawn of existence. When we talk about the beginning of the universe, we mean a specific moment. It is not just the start of Earth or our sun or even our galaxy. It is the start of everything that constitutes our cosmos. All the matter, all the energy, all the space we see around us today, and even the vast expanses of space that we cannot yet observe. Before this monumental moment, scientists believed there was nothing in the way we understand nothing, or at least nothing as we currently define it through physics. It's a mind-bending idea, isn't it? To think that our vast, sprawling cosmos had a definitive starting point, a single, incredibly powerful genesis. Trying to understand this beginning takes us on an incredible journey through time. Let's delve into the captivating story of our universe's birth. So, what is this Big Bang that we hear so much about in cosmology? The name itself can be a little misleading, you see. It might conjure up images of a giant firework exploding, a colossal fiery explosion happening somewhere within a pre-existing empty void. But that is not quite the right picture to hold in your mind. The Big Bang was not an explosion space, like a bomb going off. Instead, it was the rapid expansion space itself, everywhere simultaneously. Imagine a tiny, infinitesimally small dot. This dot was incredibly hot and unimaginably dense. This single point contained everything that would eventually become our entire universe. This initial state of the universe was hotter and denser than anything we can truly recreate or fully comprehend. All the energy and all the matter of the future cosmos were packed tightly together. In this primordial state, there were no stars, no galaxies, not even atoms as we know them yet. There was just a seething, incredibly energetic primordial soup. This soup consisted of fundamental particles and immense energy. The very laws of physics as we currently understand them might have even been different then. It's a realm that pushes the absolute boundaries of our scientific understanding. It represents a point of origin for space and for time itself. Then, in an instant, this unimaginably tiny point began to expand, and it expanded with incredible rapidity. Space itself started to stretch out, carrying all of its contents along with it. This monumental expansion marked the true birth of our universe as we know it. The Big Bang Theory is our best scientific explanation for this incredible beginning, supported by a wealth of observational evidence. The very first moments immediately after the Big Bang were truly chaotic and unimaginably energetic. We are talking about incredibly tiny fractions of a second here. In this extremely brief period, the nascent universe was a whirlwind of intense activity. The temperature was trillions upon trillions of degrees Celsius, far beyond anything we can replicate. Fundamental particles were constantly being created from energy and then annihilated back into energy. It was a state of pure, raw, seething energy, unlike anything we experience in our everyday lives now. The four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces may have been unified. They might have acted as a single, all-encompassing superforce. Then something truly extraordinary and pivotal happened, a period that cosmologists call inflation. For a fleeting moment, starting around an incredibly small fraction of a second, approximately 10 to the minus 36 seconds, after the Big Bang, the universe underwent an absolutely astonishingly rapid and exponential expansion. It grew at a rate that was effectively faster than the speed of light. Now you might correctly think that nothing can travel faster than light, and that is indeed true for objects moving the fabric of space. However, cosmic inflation was the expansion space itself. The fabric of space-time can, and in this case did, expand faster than light could travel through it. It was a truly mind-boggling and transformative event in cosmic history. This inflationary period, though incredibly short-lived, was immensely important for the future structure of the universe. It stretched the universe from a size smaller than a subatomic particle to something perhaps as large as a grapefruit. This rapid and extreme stretching had a profound effect. It smoothed out any initial irregularities or wrinkles in the fabric of the universe. The universe truly took a giant, formative leap in its very first breath. After the incredible and transformative burst of cosmic inflation, the universe continued its expansion. But now, the rate of expansion was at a more sedate and manageable pace. As the fabric of space stretched ever outwards, the universe as a whole began to cool down significantly. This cooling process was an absolutely critical step in cosmic evolution. It allowed for the fundamental particles which were created in the initial chaos of the Big Bang to start combining. The extreme, unimaginable heat of the very early moments had kept them flying apart. It was like a frantic, energetic dance where partners could never quite hold on to each other. Now with the cooling, things were calming down. The universe was preparing for its next grand act, the creation of the first atomic matter. As the temperature of the universe dropped further, quarks and gluons, the fundamental constituents of protons and neutrons, could finally bind together. This pivotal moment happened when the universe was just a few microseconds old. Protons, which carry a positive charge, and neutrons, which are neutral, began to form. These are the essential building blocks of all atomic nuclei. An interesting detail is that for every billion particles of antimatter, there was roughly one extra particle of matter. This slight, almost imperceptible imbalance was absolutely crucial. When matter and antimatter particles met, they annihilated each other in a brilliant flash of energy. What was left over from this cosmic battle was the matter that makes up everything we see around us today. For the next few minutes, from about 3 minutes to 20 minutes after the Big Bang, the entire universe was like a giant nuclear fusion reactor. The temperature was still incredibly high, hovering around 1 billion degrees Celsius. In these conditions, protons and neutrons began to fuse together in a process called Big Bang nucleosynthesis. It was during this relatively brief but crucial period that the very first atomic nuclei were forged. The universe had successfully forged its first essential building blocks, a truly monumental step in its ongoing evolution. Even though the first atomic nuclei, primarily hydrogen and helium, had successfully formed, the universe was still a very different place than it is today. For hundreds of thousands of years following the Big Bang, it remained a hot, dense, and completely opaque fog. Imagine being trapped inside a very thick, soupy cloud, but one that is incredibly hot and glowing. Light, in the form of photons, could not travel very far at all during this epoch. Photons were constantly bumping into and scattering off charged particles. These were primarily the free-roaming electrons and the newly formed hydrogen and helium nuclei, which are ions as they lack their electrons. These charged particles scattered the light relentlessly, making the universe like a glowing, impenetrable soup. As the universe continued its relentless expansion, it also continued to cool down steadily. This gradual cooling eventually reached a critical milestone for the cosmos. This occurred around 380,000 years after the Big Bang. At this point, the average temperature of the universe dropped to about 3,000 degrees Celsius. This was cool enough for a crucial event, known as recombination, to take place. Electrons, which had been zipping around freely in the hot plasma, could now be captured by the hydrogen and helium nuclei. They combined to form stable, electrically neutral atoms. This was an absolute game-changer for the universe. The dense, obscuring fog was finally about to lift, allowing light to travel freely. With the electrons now bound into neutral atoms, the universe suddenly and dramatically became transparent to light. The photons, which had been constantly scattered by free electrons and ions for millennia, were now free. They could travel unimpeded through the vastness of space for the very first time in cosmic history. The discovery of the cosmic microwave background radiation in the 1960s was monumental. It provided strong evidence supporting the Big Bang theory, like finding faint, warm embers from a colossal cosmic fire. This CMB is not just a uniform glow. Satellites like COBE, WMAP, and Planck mapped it with precision. They found tiny temperature fluctuations crucial for cosmic structures. These ripples are the primordial seeds for future cosmic structures. Slightly denser regions attracted more matter over billions of years. They grew to become the first stars and galaxies, forming the vast cosmic web of galaxy clusters we observe today. Studying the CMB reveals the blueprint of our universe. It tells us about its age, composition, and geometry, an invaluable treasure trove of cosmological information. From that first light, gravity sculpted the primordial matter, creating the first stars and galaxies and eventually the universe we see today.